All right, so here we go. Inverse of exponential functions. So you were practicing doing your delta math, doing a little practice with exponent rules, right? Yeah, all that good stuff. Exponential functions are a little different in regards that our variable is our power instead of our variable being our base, which is what you were practicing. A lot of times, students have the tendency to mix up those rules with what we're doing as a function. And I need you to learn to separate, which is why you were practicing using the rules versus analyzing the function. Does that make sense? Sure. Okay. Your do now had you analyzing an exponential function. Your delta practice had you utilizing the exponential rule, exponent rules. Make sense? If you are stuck on the rules, there's a little poster chart above the turn-in box that has all the exponent rules written out in one place. If you want to take a look at it, take a picture of it. But it is all of the exponent rules written in one space. If you still have your Algebra 2 notes from last year, there's also notes in there. But I don't know if you still have your Algebra 2 notes or not, but it's okay if you don't. Okay, so let's dive in. So we're on to 2C.10, and we're going to be talking about the inverse of an exponential function. And if you remember from Algebra 2, that inverse is called a logarithmic function. Yes? Sounds familiar? Inverse log. So because exponentials and logs are inverses of each other, we will expect their characteristics to be the opposites of each other, right? So the domain and range of the exponential is the range and domain of the log and vice versa, right? Because your inputting or output are changing. Therefore, your domain and range are also switching and flopping around. Whereas exponentials have horizontal asymptotes, logs have vertical asymptotes, correct? Exponentials have a y-intercept, logs have a x-intercept, okay? Their properties are opposites. So when we look here at this, we know that it's an exponential function because over equal with input, meaning that my input is equally divided, so, or equally spaced. Notice I'm going from here to here, 1, 2, 2 plus 2 plus 2. Where is my pen? Am I on it? Plus 2, plus 2, plus 2. That's what it means, equally with input values. And the output values are changed multiplicatively. So I'm multiplying by 2, multiplying by 2, multiplying by 2. That's how I know that this represents an exponential model. Yes? Okay. Now, how do I know it represents a log model? The log model is going to be the opposite of it. Okay. For a log model, what's going to happen is that your input are going to have a multiplicative change. Your output are going to have the equal with value. So when I look here, my input is going multiplying by 2, multiplying by 2, multiplying by 2. My output is where I am adding to, adding to, adding to. That's how you can tell from a table whether you have a log or an exponential model. Do we see the difference in the patterns? Yeah? All right. So if you really see the difference, I'm going to pause and give you a moment to determine whether A, B, C, and D are exponential models or log models with your group at your table or nearby here. Go. Hulu, Paramount Plus, Peacock. Oh, my LG. All right, here we go. On exactly. I was like, what? I was confused. All right, what is A? A is exponential. Why is it exponential? There we go. Perfect. All right, what is B? Perfect. And why is it so? Perfect. All right, what about C? Ooh, I didn't trick you. Perfect. And that's because both are being multiplied. All right, and then D. Log. Perfect. And why? Perfect. There we go. All right. Yes. Can we identify from a table? Geniuses. Moving on. All right, on to the next part. So exponential and log functions as inverses mean that when you are doing composition, when you compose them into each other, then the output's going to be x. That's the rule for any inverse, right? If I plug an inverse into itself, an inverse to its inverse, it's going to give me x, meaning the composition equals x. So when we are graphing and analyze, there's two things that we need to remember about inverse functions. Graphically, they're going to be a reflection over that imaginary y equals x line, right? If I fold along the diagonal, they should touch each other, correct? And if the point xy1 is on one graph, then its inverse y1 x1 has to be on the other. Otherwise, they are not inverses of each other, okay? So let's look at an example here. So we want to verify whether 3 to the x and log base 3 of x are inverses of each other, okay? Naturally, we already know this, correct? We do. But we're going to show how composing will prove that they are inverses as well. When we compose, the end result needs to be x for both compositions, all right? So we're going to start off with f composed of g of x. G of x is log base 3 of x. F of x is 3 to the x. So that means in f of x, where the x is, I am plugging in log base 3 of x. Yes? All right. I don't have enough. I didn't leave myself enough room, so I'm going to just scoot out a little bit. All right. So we have 3 to the log base 3 of x. Going back to Algebra 2 on our log properties, if the base of your log and the base of the exponent are the same, what do they do to each other? They cancel out, and I'm just left with x. Oh my gosh, it worked for the first one. Okay. Now I'm going to do the second one. The second one, I am plugging f of x into g of x. So that means I'm taking this guy and plugging it into x. So this is going to lead me to log base 3 of 3 to the x. Again, log properties. If the base of the log and the base of the exponent are the same, what is going to happen? Cancel out, and bam, they equal x. Okay? Because this happens, I know that f of x, I need to change the thing, my pen now, because it's starting to do crazy things. F of x and g of x are inverses. Bless you. Make sense? Okay. So when we're proving whether they're inverses, we use composition. We plug one function into the other, evaluate using all of our rules and properties that we know to get it down to its simplest form. The simplest form has to equal x. If the simplest form doesn't equal x, then they are not inverses. If it does, then they are inverses. Capiche? All right, let's take a look at it graphically. So graphically here, if I am graphing the inverse of a function, that means that it's going to be reflected across an imaginary line of y equals x. So this is my imaginary line, y equals x. So currently graph, we have k of x. K of x is our exponential function 2 to the x. If I want to graph log base 2 of x, I'm going to choose points on here, and I'm going to reflect them across the y equals x. Reflecting across the y equals x means that your x and y are switching places. That's what happens when you reflect across the y equals x. All right, so I'm going to obviously go here. This is a good point. This is a good point. You get the gist. These are too tiny for me to do. All right, so instead of being at 0, 1, I'm now going to be at, man, I really need to fix my pen. I'm going to be at 1, 0. Instead of being at 1, 2, I'm now going to be at 2, 1. Instead of being at 2, 4, I'm now going to be at 4, 2. Okay. The other thing to pay attention to is that you had a horizontal asymptote, right? Yes. I had a horizontal asymptote at y equals 0. What is the opposite of a horizontal? A vertical. So I'm going to have a vertical asymptote at x equals 0. And then I'm going to do my best to follow my asymptote and connect my point. And you're going to pretend that those are symmetrical. Ta-da! We can graph inverses. Okay, the last part of 2C. Any questions about graphing the inverse? Okay, the last part here is, can you analyze by finding the average rate of change over a given interval, which goes back to all the way back to unit 1, right? In the beginning of unit 1. So we have the exponential function h of x equals a to the x, contains the points 2, 3, and 6, 27. Find the average rate of change of log base a to the a of x, meaning that notice that they don't give me the value of a. It doesn't matter. What matters is what they gave me is the output from the exponential. If that is my output for my exponential, then I can automatically find the output for my log. Does that make sense? If my exponential point is 2, 3, that means for the log, I have 3, 2. If my exponential point is 6, 27, that means for the log, I have 27, 6. Which is why it's asking me to find the average rate of change from 3 to 27, because for the log, 3 and 27 are my input values. They're my x values. And now we're just going to A-rock it. And how do I find average rate of change? Well, average rate of change is the change in your y over the change in your x, right? So the change in my y, so 6 minus 2, change in my x is 27 minus 3. What is 6 minus 2? What's 27 minus 3? And 4 over 24 reduces to 1 over 6. Okay, so you had everything you need to calculate that. It was just making sure that you understood the rules and what it meant to be an inverse. Are you with me? Make sense? All right, what are your questions for 2C.10? Because h of x gave us these points. And log base a of x is its inverse. And because they're inverses of each other, that means that if these points are on the exponential, then these points have to be on the log. Yep, like we do on the graph. Exactly. You would reverse it. Reverse, reverse. Would be 6. You're geniuses, guys. Geniuses. I knew it all along. Yep, I did. You just was